The notion of mediation is hinged on this fact that, or this idea that some variable x, which we think of as a causal agent of some kind, doesn't necessarily have to be causal in a formal sense, but normally we think about mediation as a causal process, that it's linked in some way to some outcome of interest. The cause is x, the outcome of y is y, and that the reason why that relationship exists is that it's established through a series of events, a chain, sort of a causal sequence of events in which x influences some intermediary variable m, and then that sort of follows through and carries its effect through to the ultimate outcome. So these intermediary variables could be any conceivable thing you can fathom that might be relevant to your own area of work. It could be some kind of a cognitive process that X kicks in that ultimately ends up influencing Y. It could be some kind of an emotional response. It could be some kind of observable behavior. The idea is that this link from X to M to Y is a mechanism that accounts for how X influences Y in some fashion. These, as I mentioned, are quite, the simple mediation model is very much an oversimplification, but it is worth talking about, and it's also very commonly found in the literature. I'm going to just flash up a few screenshots of figures from various articles in various journals just to illustrate that we're talking about something that is fairly common, albeit, as I've now said for the third time, a bit of an oversimplification of the complexities of most things that we study. You will have a hard time actually reading any literature without coming across these kinds of figures. They're just in abundance everywhere, and I've got a library of at least 100 or more of these images. I only pulled out a few that were relevant to health. To tailor a little bit of this to my audience here, I want to just bring a couple of examples to you that I pulled from things that might be relevant to the kinds of things that Hispanic Health Disparities Research Center does. So here's an example coming out of Child Development in 2003. You're going to see in the theme, I got kind of hooked on the idea of acculturation as I was investigating this talk. So all my examples have acculturation as that causal agent. So here's a study of several hundred Mexican-American adolescents from the Houston area. And this is a model in which they argue that acculturation, or sort of greater Americanization, results in family conflict. And that conflict in turn translates into an increased likelihood of substance abuse and deviancy. Along the same lines, implied in, I think, in this is that there's a conflict that occurs between the adolescents and the parents, who maybe are acculturated to different degrees, and this kind of conflict between acculturation levels can engender some kind of family conflict. And this study more directly gets at that issue. This is a longitudinal study, actually, of over 1,700 ninth graders in LA. And they found that the greater the discrepancy between a child and the parent, more specifically the sort of more Americanized that the child was relative to the parent, the lower the family cohesion, and that family cohesion in turn translated to adolescent substance use. And then here's a third example. This is a study of pregnant Mexican and Mexican-American women in Colorado. And here this model argues that acculturation results in lower infant birth weights and other sort of negative pregnancy outcomes, because acculturation increases stress. And that in turn has these negative consequences such as premature birth and low infant birth weight. So people that are doing work in the areas that might interest you are certainly thinking about these fairly simple mediation type processes. So it's worth spending a little bit of time talking about some of the mathematics and the mechanics behind these kinds of models, what's underneath it, what's kind of assumptions, and what kind of inferential tools do we have available for understanding these kinds of processes. So, important thing to keep in mind when thinking about these kinds of models. These are causal models. More specifically, however, when we think about this intermediary variable m, or what some people call a mediator, this has got to be causally located between x and y. So the idea is that this is a causal chain of events in which x somehow influences m, and that m in turn influences y. So m is causally located between x and y. If you can't make that argument, at least convincingly enough to you and a few people who read your work, it may not be that you're dealing with really a causal mediation process. It may be something else. Maybe you're conceptualizing or conceiving this intermediary variable as something other than that. Now, one thing that I get a lot of email from people who use the tools that I've created, and one of the themes of those questions is it okay for me to do this kind of stuff that you advocate when my data aren't clearly, aren't able to clearly establish causal association? So it may be just a purely correlational study, something non-experimental. And people are always happy to hear my perspective on this, I think, because essentially I say, absolutely, you can do whatever you want to with your data. You should not be constrained at all on the kind of analytical tools that you bring to your data analysis tasks merely because of the fact that your data are correlational in nature. These are just mathematical tools. They're ways of making sense of some of the chaos that probably appears in your data, trying to discern some kind of order among the randomness. Sometimes the best that we've got for sort of hanging our causal hat is the best we've got for hanging our causal hats is our theory. It may be that we can do nothing other than try to make a good logical argument that these relationships are causal, even though you maybe can't empirically establish them as such. So I have no problems with using the kinds of analytical tools that I'm going to talk about today with data that are correlational in nature. Ultimately, it's your responsibility to make the argument, make it convincingly, and couch your interpretations with the appropriate sort of cautions and caveats and so forth. I want to start off with a very brief tutorial of the elements of path analysis. And this is important because it really serves as the foundation for things that get to be more complicated later on today. And I'm going to be talking about everything in the context of ordinary least squares regression, or more generally, I guess you could talk about it in terms of any linear model that you might estimate with a structural equation modeling program or anything else. The method of estimation itself is not that important. But we are going to be dealing today entirely in the realm of observed variables. That is nothing latent, although these principles certainly apply to latent variables as well. And we're not going to do anything involving dichotomous outcomes or mediators. We're going to strictly be focusing ourselves in the realm of continuous observed measures. We could talk at some point about the limitations of applying these ideas to other sort of more complicated or messy data. But we're gonna for this point, for this talk at least, focus purely on these sort of relatively simple and pure observed continuous variable models. X, by the way, can be dichotomous, no problem with that. So if you think about regressing y on x, so y is some outcome variable of interest to you, could be some health outcome like infant birth weight, and you have some variable x which you think is causally influencing y. Maybe it's some measure of acculturation. You want to estimate y from x, you can calculate a regression coefficient to quantify that association. And we're going to be talking about things purely in unstandardized form. Right now we can talk about things in standardized form, although I tend to prefer to stay away from standardized metrics when I talk about and teach and write about mediation for problems that I won't, for reasons I won't get into right now. So if we were to regress y on x, we'd get this thing C. So so imagine regressing y on x, that's this equation here. This thing called C, this coefficient I've labeled C is called the total effect of x. Now imagine that we propose some intermediary variable m that is accounting for the causal influence of x on y. In that earlier example, it was stress, cortisol levels. So let's predict cortisol levels from x, say acculturation. That's the second equation here. And from that, we can get an unstandardized regression coefficient A. And then imagine now a third model in which we estimate some outcome y, so maybe infant birth weight, from both the intermediary variables, so cortisol levels, as well as the presumed causal agent, in this case, acculturation. That'll give us B and C, these unstandardized regression weights from that regression coefficient. And it turns out, mathematically, and this will always be true, you can't make it not true. It turns out that coefficient C, the total effect, partitions nicely into two components, what we call the direct effect of x on y and the indirect effect of x on y. Again, this will always be true in the realm of OLS regression, continuous y and x. Always be true. You can't make it not true. So the total effect breaks into these two components, the direct effect and the indirect effects of x on y through m. The direct effect itself is fairly simple. That's simply the effect of x on y controlling for m. So it's that partial regression coefficient for the third model. It tells us the relationship between x and y independent of m. The indirect effect is the product of two coefficients a and b. So take the a coefficient from the second model, multiply it by the b coefficient from the third model, and you get the indirect effect. And it has a fairly simple, straightforward, and interpretable, it's a fairly straightforward and interpretable metric, and I'll give you a specific example of that in a minute. A little bit of algebra shows that means that the indirect effect, which is going to be so central to mediation analysis as well as conditional process modeling later on, is actually the difference between the total and the direct effect. So those of you who already have some familiarity with mediation analysis might know that this difference between C and C prime is important. Well, what you're talking about really is the indirect effect. Although you may not have conceptualized it or thought about it in those terms, that's exactly what you're looking at. This is a more complicated form of the model. Normally, we think about the error terms on the ends of those equations as just sort of nuisances that we get rid of. So I'm going to talk most of today in the context of this idea of estimations of y and m, where we don't worry about the error term. We know that it's there, and we express things in terms of estimations rather than the actual values. That's the reason for the little hats over the y and m in this version of the figure. Throughout today, I'm going to be relying entirely on a particular data set. Now, this is not directly relevant to the work of the center, but it is at least in the domain of health psychology. This data set comes from Germany, and these are 265 employees of a railway company. They were measured twice, with a 1 month period separating them. And there are three measures here, actually four, that are going to be relevant for today. They were getting this issue is why is it that intentions and what is it about intending to do something that leads people to actually do it? What's the sort of mechanism at work? And as we'll see as we go through this, they were proposing that this idea of planning is important, that merely to intend to do something is in itself, that this creates in people a sort of planning. They want to think about if this is something they intend to do, well, how are they going to actually carry out that behavior? And what are the potential boundaries to carrying out that behavior, and how can they plan in advance to make sure that they don't end up being inhibitors to the behavior that they intend to do? So we have four measures here. One is an intention measure. These people are asked a bunch of questions with respect to their intentions to engage in strenuous physical activity during their leisure time. We also have a measure of physical activity. This is how much they actually did engage in vigorous or strenuous physical activity in the last week. And then there was a measure of planning for how, when, and where one is going to actually be physically active. So it contains this thing called an activity. I have the terms. It's action was sort of an action component. What am I going to do? Where am I going to do it? How often I'm going to do it, and so forth. And then also a dimension which also hints into sort of how am I going to get around the obstacles that occur in my life that might stop me from doing this? How will I sort of plan in advance to make sure those things don't stop me? But this is all ultimately in a single unidimensional measure of planning. And we also have age measured in years. Where we're moving toward ultimately is answering this question: is the intention to behavior link mediated by planning, and does this indirect mechanism vary systematically as a function of age? So that's a question of the contingent nature of the mechanism. That's where we're ultimately moving toward. Okay, so you're going to see this data set. You'll see this data set after lunch, and actually you may have already seen it if you downloaded and unzipped the file that you were sent early on. If you didn't, don't worry about that. I have the files here, and we can make sure that you have them when you need them. But using that data set, so we're going to predict their physical activity at the second time period from their intentions to engage in physical activity at the first time period. Remember, there's a week-long period between, a month-long difference between the two measurement periods. So we'll regress y on x, that's activity at time 2, on intentions at time 1. And we'll get a regression coefficient. And in this case, that turns out, as you'll see, to be 0.478. I'll give you an interpretation of what that means in a minute. We then regress the proposed intermediary variable planning. That's planning at time 2 from their intentions at time 1. The idea being that their intentions initiates a planning action. And that regression coefficient is 0.43, predicting planning from intentions. And then we predict activity at time 2 from both planning at time 2 and intentions at time 1. You get B and C prime. Those are both about 0.3. Again, you'll be able to replicate these on your own after lunch, and you'll see that I'm not lying to you. And the point of this is to show you that the mathematical relationships I just described to you are in fact do hold. Notice that the direct effect, that thing we called C prime, 0.335, and the indirect effect, which is the product of A and B, in this case 0.43 times 0.33 or 0.143, you take the direct effect and the indirect effect, you add them up, and you get the total effect. That will always be true. Okay, and this is just to show you that I wasn't joking. This actually is true, and it will always be true. So what does this mean exactly? How do we interpret these effects? Well, in a generic sense, we can talk about it without giving any particular context. So we could say the two people who differ by 1 unit on x, whatever that metric is, whatever that metric of x is, are estimated to differ by total effect units on y on average. Furthermore, they differ by indirect effect units on average as a result of the effect of x on m, which in turn affects y. That's the indirect effect. And then the rest of the difference, the rest of the total effect, that difference of direct effect units is due to the effect of x on y independent of m. So if we put this into this specific context, we can say this. Two people who differ by 1 unit in their intention to exercise differ by 0.478 units on average in their physical activity 1 month later. And the sign tells us that the person who with higher intentions exercises more later. They differ by 0.143 units on average as a result of the effect of intentions on planning, which in turn affects physical activity 1 month later. That's our indirect effect. And then the rest of the difference is due to the effect of intentions on later activity independent of planning, or the direct effect. Now, as I mentioned to you, I have no problems with employing these kinds of tools with correlational data, but of course correlational data are replete with all kinds of alternative explanations, among the possibilities being a variety of numerous confounds. It turns out that that's not that difficult to deal with if you have measures of those confounds. And the point of what I'm showing you here is to show you that if you partial any conceivable confounds out of both m and y in the model, you'll end up with exactly the same relationships between the total and the direct and the indirect effects. So imagine we have some variable u, which we think might be accounting for the associations through some kind of a spurious or epiphenomenal type of pattern of associations. Well, let's just put it in the models of y and m. I've placed the lines and boxes for the covariates there in light gray, only to symbolically show that we don't really care that much about them. We just want to get those relationships out of the associations of interest to us. When we do that, when we include these potential confounding variables in the models of both y and m, we will still find that the total effect partitions cleanly into the direct and the indirect effect, the indirect and the direct components. Now, these are not going to be the same as the direct and the indirect effects when you don't partial those confounding variables out. We don't have a name for them. I guess you could call them sort of partial total effects if you want to think about them that way. They're relationships after partialing out confounding associations. So when you have information at prior time, in the case of this example, oftentimes those prior measurements pick up a lot of things that can account for relationships spuriously. So in this case, I've thrown in earlier activity, that is activity at time 1, as well as planning at time 1. I've partialed those out of all of the paths. Simple enough, just include both of those time 1 measures in the models of both y and m. And here is the results when you do that from those various regressions, and you'll see that indeed the total effect, which is 0.245, partitions cleanly into the direct effect and the indirect effect, just as promised. What I want to do now is talk a little bit about old school or old millennium approaches to thinking about mediation analysis and compare them and contrast them a bit with what I call the new millennium way of thinking about mediation analysis. This is sort of more of an oratory hook, I think, than reality in a sense. I mean, it's roughly around the turn of the century in which there was this sort of vast explosion in the literature, in the methodology literature about mediation analysis that really started to question the way people had been doing things in the past. So that's why I bring the sort of old versus new millennium distinction in. Of course, that's sort of a broad overcharacterization perhaps of the evolution of the literature, but I think more or less reflects the fact that something happened sometime around the earlier part of I guess now the prior decade. This old millennium way of thinking goes by various names. One of them is the most popular one, or the most generic name, the one that's least offensive, I suppose, is the causal steps approach. And when I say at least offensive, I mean least offensive to Barron and Kenny, who are the ones that made it most accessible in a very, very popular 1986 article published in the Journal of Personality and Social Psychology, where they describe the causal steps procedure in quite elaborate detail. It does have its origins earlier. If you trace the origins of those steps they describe, they go back to somewhere in the 1950s. The idea of this pre-turn of the century way of thinking about mediation analysis is that although the indirect effect ultimately is what we care about, we actually never quantify it formally. Instead, we just infer its existence logically with a bunch of hypothesis tests on the individual components in the model. What you'll see is that we don't do things that way anymore. After the turn of the century, what has shifted is that there's been a much stronger emphasis placed on the indirect effect itself, because ultimately it's the quantification of the mechanism. The indirect effect is our empirical quantification or instantiation of the mechanism itself. We also don't use inferential techniques now that make unrealistic assumptions, and as a result of that, we buy ourselves some power, meaning if there's something out there to find, you'll find it with greater likelihood if you use these newer approaches. What is one of my more important lessons, I guess, for you to take away from this is that nowadays we don't care so much about the individual paths in the model, whether a particular path is statistically significant or not, for instance. That's just not a part of the argument you put together. And when things get really exciting toward the end of my lecture is when you start thinking about indirect effects as things that can be modeled. And in order to model indirect effects, you need to quantify them. But once you start quantifying indirect effects, then you can start asking, well, what circumstances predict the size of these indirect effects? What kinds of individual differences, what kind of contexts, what kinds of people do you tend to find indirect effects that are large versus small, and so forth? Talk a little bit about this old millennium approach. And it primarily focuses on the idea that we want to account for the effect of X on Y by identifying mediators of the effect. So we have some association between two variables X and Y, and we want to know why do these relationships exist? What are the things that are intermediary or between that account for them? With the ultimate objective being that we want to label these mediators. We want to first say, is it the case that M is a mediator, and if so, does it completely account for the effect of X on Y, or does it only partially? The idea of the causal steps approach is that we are going to essentially see whether our data pass a variety of tests. And we establish these criteria that would allow us to say that M is functioning as a mediator. And we have to pass all three of these, or there could be four depending on how you think about the criterion. My wife tells me I should try not to move around so much, but I gotta tell you, I'm busting loose. It's really hard for me to stand still when I talk. So by the causal steps criteria, we try to establish whether certain criteria are met. First thing we want to do is we want to establish, is it the case that X affects M? The reason why I'm partially back, is it possible for you to step away from the mic and still hear this? You need this. Okay, I'll stick to it. It's probably better in your case. I'll just distract you by pacing around. All right, so do we have evidence that X affects M? And the test of that is merely a hypothesis test. Do we have evidence that X is significantly associated with M? Let's not worry too much about the criteria of causality. We're going to think those are really not statistical issues. Those are design issues. So do we have evidence that X affects M? So is A statistically different from 0? Does M affect Y holding X constant? In other words, is path B statistically different from 0? And then the third criterion, actually, although in a sense this is a confounding of a sort of step 0 with step 3, and these are the words of Baron and Kenny: a previously significant effect of X on Y. That's path C. So in other words, we've already sort of established that there's a relationship there. If we didn't establish that, we wouldn't have bothered with the first step in the first place. So a previously significant effect of X on Y, that's path C, or the total effect, is reduced when M is held constant. In other words, is the direct effect closer to 0 than the total effect? And the significance of C prime is what determines whether we talk about X's effect as being completely or partially mediated by M. So if C prime is essentially not different from 0, then we would say, well, M totally accounts for the effect of X on Y. M is a complete mediator. But if the direct effect, C prime, remains statistically different from 0, we would say, well, that association between X and Y that we observe, the total effect, is only partially accounted for by this mediator. So if we were to apply the causal step strategy to the physical activity data, what we would find is that all 4 criteria are met. We do have evidence of X affecting Y in a statistical sense. That is the total effect is statistically different from 0. We have evidence of M being related to X and Y being related to M, controlling for X. And the direct effect, C prime, is closer to 0 than the total effect, but it's still itself still different from 0. So this is what people would label as as partial mediation, according to 20th century lingo. So there's still some association between attentions and activity that's presumably accounted for by some other mechanism. Whatever that mechanism is, it's not planning, because after you account for planning, there's still an association between intention and activity. Now, there's some things about this, when you stop and think about it, that are a little disturbing if you think too long about it. Now, notice all this talk about the indirect effect as being this instantiation of the mechanism, and yet nowhere in this procedure have we actually ever quantified it. Right? So we're just sort of logically inferring the existence of a direct effect. of an indirect effect. And what I find to be somewhat curious about this is that that's not normally how we do things in science. Normally, we quantify effects of interest and establish through some kind of an empirical approach or inferential tool as to whether we have evidence that that effect exists. So when we want to compare groups, we calculate some difference between them on some metric and ask, is that difference different from 0? When we want to correlate two things, we will correlate them. We measure and we quantify the association. We ask, is there evidence that this relationship exists? Why should indirect effects be any different than that? So there's a sort of inconsistency between the causal steps approach and the way that we... Sure.
Looking at the path analysis, you actually did estimate that indirect effect, right? So could you clarify what you mean there?
What I mean is that there's no attempt to actually quantify it in a formal sense of saying the indirect effect is this. You're going through the mechanics of the estimation, but never actually taking that last step, quantifying it,
and then applying an inferential test to it. So yes, you're definitely going through the mechanics, but you're just sort of going through the motions in effect, because ultimately, by the causal steps criteria, you're not interested per se in the indirect effect itself. Now, the rebuttal to this is that, well, if the indirect effect is the product of A and B, and we have evidence that both A and B are different from 0, then why do we need to bother thinking about quantifying or doing an inferential test on the indirect effect? It must be different from 0 if both A and B are. There's no other way that it could be. And it turns out, I mean, that in a sense that's true, but it's not necessarily true. It will often be true, but it's not necessarily true. So in other words, there could be circumstances in which the indirect effect is actually not statistically different from 0 using some sort of newer and legitimate approaches to inference, even though A and B are both different from 0 according to hypothesis testing procedure. But I think what's even more important, probably from your perspective, is that it may be the case that there is an indirect effect in your data, but you may not have been able to meet the criterion that A and B are both different from 0. Okay, so in other words, a more modern approach to thinking about things and conducting hypothesis tests on indirect effects may lead you to claim there is an indirect effect, even though you can't say that both A and B are themselves different from 0. So if you're following along, I'm talking about power ultimately. And I think that power problem that's attached to the causal steps strategy is because of its over-reliance on these sort of imperfect inventions of the human mind, these decision steps that we engage in known as hypothesis testing, right? These are just probabilistic procedures. They're not perfect. They make mistakes. We know they're going to make mistakes. We teach the theory of the mistakes in any intro stats course. So when you do more of these tests that you do, the more likely you're going to make a mistake somewhere. So it makes scientific sense for us to minimize the number of tests that we do to be able to support a scientific claim. So one of the most important things, takeaways I've noted already, is that we should not be thinking about we should not be thinking about mediation with respect to whether we have evidence that every little part of the path, whether we have evidence of the existence of some effect at every step along the way. That's just not a part of modern thinking about mediation analysis. This is all contingent on the existence of an effect in the first place, right? So if you don't have evidence that X and Y are associated in some fashion, then you don't even bother starting down the mediation pathway. You don't even start down the causal steps path. And that makes some sense if you think about one definition of a mediator. So the idea that a mediator, and this is a common definition, it's out there, it's a variable that's causally between X and Y that accounts for their association. Well, if there is no association, then how can there be something to account for? It turns out, however, and the world, at least my world, has increasingly converged on this belief. It turns out that the total effect, its size or its significance, is totally irrelevant with respect to whether you can establish evidence of an indirect mechanism. The significance of C, that is the total effect, doesn't constrain, doesn't influence in any way the product of A and B, nor does it tell us whether A and B is different from 0 when you multiply them together. So there's just no information that's really carried about the indirect effect by whether C is statistically different from 0 by some kind of a hypothesis testing procedure. But ultimately, where I'm going with this is that in order to do really sort of where things are going in the modern mediation analysis world, is you have to think about indirect effects as quantities that are worth, well, actually quantifying, because once you do that, the analytical world opens up in terms of the possibilities available to you. So the Barron and Kenny strategy, the causal steps approach, really makes us think about things in sort of a dichotomous way, and in some ways it's the way that we think, right? We talk about science, we don't like to think about the uncertainties that are inherent in things like confidence intervals. We like to sort of think, is there an effect or not? But that's not the way the world works. That ultimately things are continuous in the world, and when we start modeling indirect effects as continua rather than as either existing or not, we're in a better position to more understand the complexities of the world that we live in scientifically. So I'll talk a little bit about the new millennium. I've sort of hinted at that already. We're going to more or less go about this thing analytically in the same way. We're still going to apply the same linear models to estimating these various coefficients in these causal diagrams. But we're going to take that extra step of quantifying the indirect effect by multiplying A and B together, and then we're going to actually conduct some kind of an inferential test on that product. It could be a confidence interval. It could be some kind of a formal hypothesis testing procedure. We're not going to worry about labeling this process. Complete and partial mediation are now 20th century terms. I think they're slowly being abandoned by people who write about and think about mediation analysis, although they're still a part of the lingo of practicing scientists. They're sort of waning with respect to the value that we, people like me, think about them having. And then again, as I've already mentioned, the hypothesis tests on A and B, or for that matter C and C prime, are not themselves all that relevant to whether there is evidence of mediation at work. Although you can supplement a discussion of mediation with inferential tests on the components of it, it's just not really a part of the story that we tell. Now, it's not true to say that nobody's been quantifying indirect effects before the 20th century. Of course they have. And in fact, Barron and Kenny talk about in their 1986 article something called the Sobel test, which is actually it's an inferential tool or test based on the product of A and B. And some people will do this. They'll add that sort of extra inferential test as a kind of punctuation on the causal steps strategy to say not only have we met the causal steps criteria, but we have also established evidence of an indirect effect through this thing called the Sobel test. It's a fairly simple test. It merely involves taking the estimate of the indirect effect and dividing it by some measure of the standard error, and there are a variety of different standard error estimators that are out there. And then you've got something that people think of as a normally distributed index, and you tag a p-value onto that using the same kind of procedures you would use in Stats 101. So we assume that the sampling distribution of the indirect effect is normal over repeated sampling from the population, and then we tack a p-value onto that to make a decision about whether the indirect effect is different from zero. What I do see people doing, again, is they sort of use this as a way of confirming what they already believe as the result, after the outcome of the causal steps strategy, and my argument would be don't do it in addition to, do it instead of the causal steps strategy, because it actually is the only thing that matters. The indirect effect is all that really matters. So why we don't generally recommend the Sobel test, and there are a lot of reasons for it. One of them, it is actually relatively low in power compared to what I'm going to talk about next. And primarily that's because of an assumption that's made that is just patently false. And that's the idea that the product of A and B is itself normally distributed over repeated sampling from the population. We simply know that that's not true. Analytically, you can prove it. You can prove it through simulation. It's just repeated sampling from a population with a given A and B generates an index that itself over repeated sampling is not normal. And when you assume it is and tag a p-value onto it, you're going to end up making mistakes more often than you appreciate. So we don't recommend the Sobel test anymore. It is better than the causal step strategy, but it is still not as good as you can do. What we do recommend are a variety of approaches, and I'm only going to talk about one, the one that I've been advocating the most. But it, again, is not the only thing out there, but it's something that is nowadays very, very simple to do, and there's really no reason not to be doing it anymore, and that's bootstrapping. Okay, so bootstrapping is an inferential tool that's been around for a long time, and it's very, very versatile. It can be used in a lot of different ways, but it turns out to be particularly handy in this circumstance. It's exactly the kind of circumstance in which bootstrapping shines over alternatives. And here's the issue. Here's why we don't like the Sobel test, right? We don't like the Sobel test because it makes this assumption that over repeated sampling from a given population, the product of A and B is normal. Well, it's not. Well, what is it? Well, it's something pretty complicated. And it's mathematically a fairly intractable distribution to work with. And even to mathematically describe that distribution, you need to make all kinds of assumptions. When you don't like to make assumptions and when you don't like to impose beliefs on the distribution of a variable over repeated sampling, or you simply don't want to, you simply want to go based on only what you know, and that's the data you've got, bootstrapping works really well. It's essentially a way of figuring out empirically what the random sampling behavior of a statistic looks like, and then using that information that you obtain empirically rather than through a bunch of mathematical assumptions or theories that which may or may not actually be consistent with reality. This has become the preferred method for estimating and testing indirect effects now, and it's not the only method, as I mentioned. There are some competitors, some that are a little bit easier in principle, but that aren't really implemented yet in software. But bootstrapping is now available in software that you use. Here's the gist of bootstrapping, and it's a sort of a simple 5-step procedure. What we're going to do is we're going to take a sample of a given size, that sample size being equivalent to the sample that you originally obtained. So if you have a sample of size n in your study, you're going to take a sample of size n from your sample. You're going to do that with replacement. Okay, so we'll take a sample of size n with replacement from our original sample. We're then going to estimate the indirect effect. And we'll do that the same way that we do it as I've described already. We can calculate A and B, regressing M on X, and so forth. We're then going to repeat this. Once we've calculated that indirect effect in that what's called a resample, we're going to repeat this. We're going to do this over and over and over and over again. And what this will do is it'll allow us to build up an empirical representation of what the sampling distribution of the product looks like. Once we've got many thousands of these empirical approximations of the indirect effect over repeated sampling with replacement from the original sample, we can derive a confidence interval for our original estimate, not for the estimate, actually for the population itself, by just figuring out, well, what are the two values that cut off the lower and upper 2.5% of the distribution in that set of k being many thousands of empirical quantifications of the indirect effect through resampling. And if that confidence interval doesn't contain 0, we'll say that's evidence that the indirect effect is different from 0. But if the confidence interval does contain 0, then 0 remains in the realm of plausibility with respect to the size of the indirect effect in the population. Just to illustrate how that works, here's the gist of it. So imagine this is your data. There's 3 variables, 10 cases. And in your data, you have an indirect effect after doing the various regressions of 0.043. Well, to build up a bootstrap sample of the bootstrap representation of the sampling distribution of the indirect effect, we're going to take a sample of size, in this case 10, from our original sample. But we're going to sample with replacement. And so we'll start randomly selecting basically rows from the data file and build up a new data file that way. And once you've got that, then you can go ahead and estimate the indirect effect in that new bootstrap sample. And in this case, that indirect effect is minus 0.018. Now here's what I mean by sampling with replacement. When we sample with replacement, a case can appear from the original data, can reappear in the resampled data multiple times. So in this case, for instance, case 3 appears twice in the resample, as does case 8. But because we're sampling randomly with replacement, there's no obligation that every case in the original data file shows up in a resample. For instance, in this case, case 7 and 10 don't show up in the resample. So we repeat this process over and over again. Here's another resampling of the data set, which generates itself another estimate of the indirect effect. So once we've done that, well, what do we do with it? Well, we're going to do this over and over and over and over and over and over and over again. In principle, there's no limit to this. I mean, the only limit really is how much time do you want to wait for the answer. But with computers these days, it's easy enough to get 5,000, 10,000 without waiting more than a few minutes, depending on the size of the data set, or a few seconds, really, for smaller samples. And you can always just let it run over while you go to sleep. And do 1,000,000 if you want that way. This is an empirical representation of the sampling distribution of the indirect effect for this particular problem. So this is 10,000 bootstrap samples taken from this original sample of 265 Germans. And what we found is that 95% of the estimates obtained through bootstrap sampling were between 0.013 and 0.089. Those are the two values that cut off the lower and upper 2.5% of the distribution. And because 0 is not in that confidence interval, that is, that does not straddle 0, it's wholly above 0, we can use this as evidence to claim that the indirect effect is greater than 0 with 95% confidence. It's sort of conceptually equivalent to, although not mathematically the same as a formal hypothesis test, although if you wanted to say, go ahead and say p less than 0.05 for that, I'd be okay with that, although technically it's not accurate. This clearly is something that's computationally intensive. You need a computer to do this. But that is not at all a problem these days. And I think the thing that Chris and I first became, we became friends and colleagues working on this particular paper, which talks about essentially what I've talked about already, this need to move away from the causal step strategy. We talk about the indirect effect as an interpretable and important quantity in mediation analysis. And then we offer a simple computational tool for SPSS and SAS that does this kind of bootstrap sampling. It's fairly limited in its features. It only allows for a single mediator. It doesn't allow you to throw in covariates. It only generates what are called percentile bootstrap confidence intervals as opposed to some alternatives, which are maybe a little bit better. But it was our first go at this, and it's turned out to sort of start this collaborative relationship that Chris and I have had that has led to other things, including the 2008 paper, which was written for a slightly different problem, but it turns out is perfectly useful even for a simple mediation analysis. We reproduced this procedure for SPSS and SAS that sort of expands the complexity of the models that it can estimate and allows you to add covariates and does a variety of other different kinds of bootstrap sampling and other things. But all that's been made obsolete by a procedure that I wrote over the last 18 months called Process, which you're going to learn about after lunch. This is available for SPSS and SAS. It can be downloaded from my webpage, and it'll be the focus of a book that I'm writing that'll be out next year that I'm writing for Guilford Press. You're going to get a little bit of intimate familiarity with Process after lunch. I'm just going to go through quickly an output that you would get from Process. And essentially what it's doing is it's just generating all these regression analyses for you. Unlike Sobel and Indirect, which give a fairly small amount of information, doesn't give anything near the detail that Process gives. And in the end, what you'll end up here with is the total direct and indirect effects, including a bootstrap confidence interval, based on really any number of bootstrap samples you want. It really is as simple as this. It's literally point and click. If you're an SPSS user, if you're a SAS user, it's a little bit more, but not much more work than that. So there's really nothing to stop you from doing this, and it really has become the most accepted approach to making inferences about indirect effects these days. I think I'm going to skip this, and I'll save this for questions later, because I know you want to know about this issue about the total effect not having to be statistically different from 0, but I'm gonna skip through that for now. I think I'm going to skip through this, because I do want to talk a little bit about moderation. I want to save plenty of time for questions, and we can deal with some of these really interesting issues, like why I don't believe in partial and complete mediation, why I think they're sort of pointless now, and other things that are controversial. Because I do want to get on to moderation, but actually I think at this point, because I've been talking for 45 minutes, maybe we can take a quick pause, because I think I'm more or less on schedule, and just see if you have any questions about what I've talked about so far, other than stuff about total effects and partial and complete mediation, because I'll talk for 10 minutes about that.
Can you say something about the legitimacy of creating 5,000 and 10,000 repeated samplings with replacement from your data set, given that some people might think that you're making up data?
Sure. Well, bootstrapping is fairly ingenious. In principle, the idea here is that all the statistical theory that we use to make inferences, whether it's hypothesis testing or construction of confidence intervals, is based on the idea of repeated sampling from the population. The unfortunate thing is that we don't generally have the luxury of repeating our studies more than once or twice in our lives, maybe. We have our data, and that's all we've got to go on. And so we use the theory about repeated sampling to make inferences about what we don't know from the only thing we know, which is the data we've got. So when we have good theory that can be applied, we can, so like the central limit theorem, for instance, which allows us to say, well, the distribution of a particular statistic is normal, or converges to normality as the sample size increases. We can trust these things because they tend to work pretty well, but in this context, it tends not to work that well, and so we need an alternative. The problem is that we don't know what the distribution of the indirect effect looks like over repeated sampling because we only have one sample. We don't know what it looks like. We can't trust the theory that we've been taught about the asymptotics, central limit theorem, all those, because they don't apply. So bootstrapping is an attempt to get around this problem by essentially, I don't want to use the term artificial because that implies fake, but it is sort of a way of hypothetically conducting the study repeatedly. So you take your data, and as long as you have faith in your data as being a fairly representative cross-section of the distributions that are being measured, you can think of that as a representation of your population in miniature. And let's now repeatedly sample from that representation of the population in order to figure out what is the behavior of the statistic, in this case the product of A and B, look like over repeated sampling. So we're not generating data, we're not making stuff up. All we're doing is we're saying, I'm going to have some faith, and you have to have that faith. If you don't have the faith, there's no point in bootstrapping. If you don't have faith in the quality of your data, you're not going to get anywhere with any method. As long as you have some faith that your data more or less represents the distributions along the populations that you've measured, you're essentially going through this process of replication to figure out what does the behavior of this statistic look like. So it's not like we're creating new data. It's not like we're taking the data and pretending like now we've got 5,000 people or 10,000 or 1 million when we've only got 500 or something like that. We're just going through this process of hypothetical replication to see what does this statistic look like over repeated sampling. So there's nothing that's fake about it. We're not cheating in any way. We're not making up data. If anything, actually, if your sample is small, you could be hurting yourself in some ways because when you've got one or two unusual data points in a data set, they can really start influencing the inferential process by appearing multiple times in these resamples over and over again. So you actually can hurt yourself in some ways. There are boundaries to the values of bootstrapping, but I think that those boundaries, as long as we know that they exist and what they are, the limitations far outweigh the benefits. I'm sorry, the benefits far outweigh the limitations. Right.
Does bootstrapping, and you kind of, I think, touched on this a little bit, does bootstrapping eliminate or lessen or even enhance the need to be concerned about outliers, distributions of your variables, kind of those traditional data screening indicators, or can you kind of not worry about it so much?
Well, in a broad sense, it's no different than any other method in that you have to have some faith in the quality of your data and that it is more or less reflective of the distributions that you would observe if you had sort of infinite resources available to you to be able to see what those distributions look like on a large scale. But, and this is a good question you've asked, and I get asked it almost every single time. And until the last month or so, I've always said that's something we need to investigate empirically. The question is how far can you push this? And I alluded to it just now. When you have a large sample and you've got an occasional outlier or two or three, usually their effects are fairly diluted, right? I mean, you've got enough well-behaved data to sort of compensate for the influence that those things can have on an analysis. But when you have a small sample, of course, they're going to exert more influence. Now, here's the problem when you're bootstrapping with a small sample is now you've got one out of 20 cases that are unusual in some sense. Well, now those cases can reappear in multiple resamples. So you could have a situation where you've got 1 in 20 cases that's sort of unusual in some sense in your original data, but now you're allowing them to reappear multiple times in a resample, and now you could have, in principle, in theory, you could have a data set that contains almost all of those unusual people, although that would tend not to happen. But they can appear 2 or 3 or 4 times with not small probability. So in principle, those outliers can influence things more when you're dealing with an empirical representation of the sample distribution rather than a theoretical. The issue, though, is how far can you push it? How small can the sample be? How unusual can cases be before this whole system breaks down? And that's an empirical question that I'm now just starting. So maybe I'll have an answer in a year or so. But we're starting to play around with that. We're doing simulations where we take an otherwise well-behaved data set and we start throwing in the usual case or two and then do this bootstrap sampling to see what effects that has. And I just don't know the answer right now.
Could you give us some suggestions of different references we could go to learn more about bootstrapping or to cite if we're applying for a grant or something like that?
Well, my webpage contains all of my work. So I guess there are 3 names in this area. There's myself, I suppose. There's Chris Preacher, and then there's Dave McKinnon. There's Arizona State. Those are the 3 that are doing it in this particular area. Bootstrapping is well established as an empirical method. It's been around for 20 or 30 years. The literature could be kind of technical. I don't think any reasonable reviewer of a grant would question the legitimacy of bootstrapping. Well, actually, reasonable people can do all kinds of unreasonable things, but I think you're on pretty solid ground as far as the legitimacy of bootstrapping in principle. If you're interested specifically in mediation analysis, then go to my website, go to Chris Preacher's website, and my book will be out, and we'll have a fairly large set of references as well.
I'm curious, bootstrapping is used some in my area, and they do the same principle that you do. Whatever your sample size is, the bootstrap samples are the same. And I'm wondering, I guess simulations would say this, because one thing that we want to do is, I'm thinking of my research, right, where I use a sample here in El Paso, but I'm really talking about the world, the entire population, and so forth. So, I mean, our variance here is probably not going to be as great as other areas. So, it seems to me that one thing, let's say we had a sample of 200, but your bootstrap sample was 100. That would give you some more variability there to maybe estimate the population beyond your local one. I'm curious why it's, in everything I've seen, the bootstrap sample is comparable to your actual sample, and why not less? Or I guess more could be the other thing. Outliers would certainly be an issue there, but
well, you're still trying to make an inference with respect to the specifics of your design, and your design includes a particular sample size. So you're trying to figure out what's the sampling behavior of this statistic in a sample of the size that I've got. Okay. So that's why you always fix this bootstrap sample, the sample size to the original sample size. Now, in principle, you could, say just, take half of the original data, but then you're mimicking sampling with a sample size half of what you originally had, and that's not part of your design. You didn't sample only 100, you sampled 200. You're not going to be able to take an unrepresentative sample and make it representative by bootstrapping. You've got to have some faith that your data reflect something about the I don't like the word population, although it's just a term that's so easy to use because everyone knows what I mean. Because I don't know what a population is. But whatever that universe of people that you're interested in studying is, you've got to feel some confidence that your data reflect that to some extent. If that's the kind of inference you want to make. We don't always want to do that. I mean, this thing called population inference is, I think, overstated. Unless you're a public opinion pollster, usually you don't care about this thing called population inference. Anything else? All right, well, I'm happy to take more questions later, but let's move on to moderation. I should be able to get through moderation fairly quickly, and I want to make sure that I leave enough time to talk about combining them because that's where things get exciting. combining moderation and mediation. We talk about moderation, now we're shifting away from understanding how an effect operates to when, or what are the boundary conditions of that effect. When is it large versus small? What are the conditions that facilitate or enhance versus inhibit an effect? So here's a graphical representation of the concept of moderation, in which we think of some variable effect of x on y as being contingent on w. Now, you would never, this is not intended to be a path diagram. You would never draw a path diagram and estimate something with an arrow pointing at another arrow. This is a conceptual diagram. It's the idea that w is somehow influencing the effect of x on y, with the effect of x on y being that arrow from x to y. So this depicts w as a moderator of the size of x's effect on y. Such a scenario, when w moderates x's effect on y, we would say that x and w interact. It's a synonymous term with moderation. Moderation and interaction statistically are the same thing. X we'll talk about as something called a focal predictor. So this is what you're interested in. You know, it could be an experimental manipulation of some kind. It could be an ethnic grouping. It could be anything. But that's what so what you're interested in studying the effect on with respect to the outcome. Whereas w is the moderator. It's the thing that influences the magnitude of the focal predictor's effect. Just a quick lesson in some of the constraints attached to ordinary least squares regression when you just include the moderator and the predictor in a regression model like this. So here's a regression model with two predictors, x and w. And I give you a specific, although arbitrary, form, 2 plus 0.1x plus 0.3w. The table on the left at the bottom contains a variety of estimations of y from x and w in combinations, and then the figure on the right is a graphical representation of that model. And the thing to keep in mind here is that B1 and B2 are what we would call unconditional effects, or what we can call a global property of a model. Regardless of what value of w you choose, what you would find is that two cases who differ by a unit on x are estimated to differ by the same amount on y, and that same amount is B1. B1 quantifies the difference between two cases who differ by a unit on x for any given value of w, and it's not conditioned on what w is. Any value of w, you'll find that the difference between two cases who differ by 1 unit on x on y hat is B1, and the same is true for B2. Fix x, and you find that two people who differ by a unit on w differ by B2 units on y. And that's true regardless of what value of x you would choose. In other words, we can say that in this model, x's effect on y is independent of w, and w's effect is independent of x. That's the opposite of what moderation is, though. Moderation is about modeling the extent to which w influences the magnitude of x's effect on y. We want to determine the extent to which x's effect on y depends on w. But this model, in which we just put x and w in, it doesn't allow it. It actually mathematically constrains the opposite. But suppose we let x's effect be a function of w. So in the top equation, I've just substituted b1, I've put this generic function of w. And a good one to think about is a simple linear function, b1 plus b3. W. So it looks like sort of a simple linear regression, except now it's not, the outcome is now this function of w. Actually, this function of w is a stand-in for x's effect. So if we substitute that linear function b1 plus b3 plus b3w in for f of w in the first equation, and then do the mathematics and distribute the x among the terms, and what you get is that bottom model. And by doing this, something magical happens. Now notice that when we have a model in which we include the product of x and w as a predictor, we now have a model that's much more flexible, in that it allows x's effect on y to be a function of w. So in this case, the expected difference in y between two cases who differ by a unit on x depends on w. It depends on which value of w you choose. So x's effect is no longer unconditional. It's no longer what we call a global property. It's something called a local property of the model. So the difference between two cases difference in y between two cases who differ by a unit on x depends on w now. It doesn't have to be that way, because if B3 is 0, and of course this reduces to the earlier model in which x's effect is independent of w. So by estimating B3, we could figure out the extent to which w actually moderates x's effect. It may be that empirically we find that B3 is 0, or so, not large enough from 0 to be statistically detectable, is different from 0. So testing B3 as an empirical quantity allows us to make a test as to whether x's effect is contingent or dependent on w. That's what moderation is. So B3 is critical. Here, when we test moderation, we want to know, do we have evidence that when we allow a linear modeling routine to weight that product by a certain amount, is that weight different from 0? If it is, that tells us that w moderates x's effect. In terms of some notation, so I've just sort of worked backwards. We take the model which includes the product, again, show that we can rewrite that model where x's effect is now a function of w. Now I just call that arbitrarily, call that theta. So I rewrite the model here where y hat is I plus theta x plus b2w. So w is now sort of the stand-in for x's effect, what we used to call b1, but now it's a function. B1 plus B3W. So theta is what we call the conditional effect of x. Another term that you'll see in the literature for this is something called the simple slope of x. It's the slope of x in a regression model, but that is conditioned on the value of a moderator. So conceptual representation of moderation is where we put theta as now the effect of x on y, where theta is a function of w. In this case, a simple linear function. Of course, you could put some other function in rather than that linear function, and in principle that works well. But the linear function is the one that's most commonly used. So let's extend this this example of German. Let's extend the sample that we were talking about earlier, where we now think about that link from planning to activity as moderated by age. So to what extent does degree of planning to engage in physical activity influence physical activity, and how much does that depend on how old a person is? So we have a measure of age in the data. It's just based on when the person reported they were born. It's a continuum. That conceptual diagram of moderation translates into a statistical diagram of, as it appears in the bottom, where we simply have three predictors of y, x, w, and x times w. That's a simple model in which we weight each variable with a certain coefficient, and we figure out what those coefficients are analytically. Simple enough to do. It's just a matter of including that product as a predictor variable along with x and w. So here's an output from SPSS where we calculate that product, and then we just include that product in along with the two variables that define the product. And what we find is that regression coefficient for the product is 0.016 and statistically different from 0, which by itself is sufficient evidence for us to say that the effect of planning on physical activity is contingent on age. Now that in itself, until you get a lot of practice, and even after you get a lot of practice, the number itself, 0.016, is not going to carry that much meaning. It's not going to be at all obvious what's actually happening in the data. You have to visualize this in order to make sense of it. So here is a graphical depiction of that model. Just to show you how this works, so at the top we have the model, again, in its full form, and then I've got it reduced down to where we think of x's effect as a function. That function is b1 plus b3w. So that's theta. On the right, I've got this table of various values of age. These are arbitrarily chosen. And we plug in age into that function, that theta, and we figure out, well, what's the effect of planning on activity for those values of age? and then the left just contains a visual representation. So the slope of each of those lines is theta given W. So for when age is 70, that steep, solid, dark black line, the slope of that line is theta, in this case 0.893, derived from that function, B1 plus B3W. So what we can see here is that it's apparent that that for among older people, more planning translates into more activity. Not so much true for the younger people. Those visual, to me, I'm usually happy enough with those. To me, this is a holistic representation of what's happening, and I'm usually happy enough with that, but most people want you to go a little bit further, engage in this exercise known as probing an interaction. We have a variety of tools available to us to do that. Really the only method that's out there that's being used routinely is this thing called the pick-a-point approach. And this is tedious to do by hand, but you may have all had the experience of getting to do this at one point in your life. The idea is that, well, we know we can estimate theta. We have estimates of B1, we have estimates of B3, we have values of the moderator. Well, let's just figure out what theta is for some arbitrarily chosen values of the moderator. And then we just need to figure out what's the standard error of that estimate. And there's a simple equation that gives us that. It's based on the coefficients and various covariances and other things that you can pull out of any OLS regression program. The kind of thing you can do by hand, you wouldn't want to, and actually doing so is certain to produce various errors in computation by nothing else other than random error, because rounding error, because you're going to not do things to 8 decimal places. Probably you're going to do it to 2 or 3, and when you're dealing with small numbers, you're going to produce all kinds of rounding error. There's all kinds of tools online that you can use to do this, and then a handy procedure for SPSS that I've written that does it for you as well. Anyway, if you do that, and I'm not going to show you the mechanics of that, and it's not very fun anyway, you could tag a p-value onto any value of theta, that is the value of planning's effect on activity for a given value of age, and when you do that, you find, and these are arbitrary values I've chosen, but among the 20-year-olds, or among a hypothetical group of 20-year-olds, as represented by the younger people in the sample, we find that there's no statistically significant association between planning and physical activity, but go up to age 30 and beyond, and you have clear evidence of a positive association, that seems to be getting stronger as age increases. Problem with the pick-a-point approach, of course, is the arbitrary nature of the selection of W, right? You could pick any values you want. Commonly, people will use, for a continuous moderator, they'll use the sample mean and then plus and minus 1 standard deviation as sort of representations of the concepts of relatively low, moderate, and high on the moderator. That's no less or more arbitrary than any other strategy that you could employ. For a dichotomous moderator, it's not as much difficulty, right? Then you just calculate theta for the 2 values of the moderator in your data. That's easy enough, and there's nothing arbitrary about that. But for continuous moderators, the arbitrariness of it is a problem. The Johnson-Neiman technique, which you probably haven't heard about, but you're going to be reading more about and seeing more people do. I've noticed a dramatic change in the last 3 years or so with respect to people doing this. Sort of turns the problem around. It says, well, let's not pick values of W, because we have no real basis for determining what values of W are meaningful. Sometimes you can, but often you can't. Let's instead ask this. At what point on the continuum of the moderator does the effect of X on Y transition between statistically significant and not? Let's just figure out what values of W define what we call regions of significance. Points of transition as you move along the moderator continuum where you have an effect that's transitioning between significant or not. And it turns out, with the help of a few people at the University of North Carolina, Patrick Curran and Daniel Bauer, that this is not that difficult of a problem. So here, in its most sort of generic sense, right? If we were to calculate theta, that's the numerator and the standard error, we'll get a t-value. And thinking in Stats 101 terms, we ask, well, is that larger than the critical t-value for a certain sample size to be able to say that that result is statistically significant? Well, let's instead say what value, let's put in a critical value of t and figure out what values of w produce exactly that value of t. What you have to do in that case is you'd have to put in a value of critical t and then isolate w in this equation. When you do that, you end up with something that's fairly scary looking, but if you remember high school algebra, that's the quadratic formula. That will have 1 or 2 solutions to it, or 0. You can have 0 solutions. Actually, it'll have 2 solutions, but it's possible that those solutions are not in the realm of real numbers. They could be imaginary. And in addition, it could be in a situation in which some of those solutions are outside of the range of your data, in which case you wouldn't be that interested in them. The point is that when you do this, you'll get either 0, 1, or 2 legitimate solutions with respect to the distribution of your data. You could have a situation in which you get 2 values or 2 solutions which define a point of transition, and there are 2 possibilities at that point. You could have a situation in which everything is beyond those 2 values are significant, but the conditional effect within those values is not. Or you could have the opposite, where the conditional effect of x is significant only inside those values, but not outside of them. You could have a situation in which you have 1 point of transition. So maybe for everybody below a certain value of w, the effect of x is significant, but for everybody above, it's not, or the reverse. Or you could have no solutions, which means it is significant everywhere. X's effect is significant everywhere on the continuum, on the moderator, or it's significant nowhere. The point is that we can do this fairly easily, albeit not by hand. You wouldn't do this by hand, but we do have computers around that can do this. Here's a visual representation of this notion of a region of significance. And this was calculated based on the data that I've just shown you. When you calculate the regions of significance for the effect of planning on intentions, what you find is you get this number 26.57. And here's a plot of theta. So that's the slope of that dark line, that function of w, and then the dotted points are the upper and lower bounds on a confidence interval. 26.57 defines the point at which the confidence interval is now above 0. Everywhere above 26.57 years old, the effect of planning on intentions is significantly positive, but for everyone below that, it's not. This is not difficult to do. We have, I wrote a computational tool with a friend of mine at the University of Vienna, where we allow you to just plug in various variables, one of which is a moderator of another, and it asks for the Johnson-Niemann regions of significance, and it spits it out to you with no effort whatsoever. Process also does this, which you'll learn about after lunch. Here's an output from Process, and I'm going to skip, well, first at the bottom, we have an implementation of the pick-a-point approach. You'll have a copy of this output later on, so you'll be able to look more carefully at it. So that's the stuff all at the bottom, where it just arbitrarily picks a bunch of values of age. And then it generates as well this table for the Johnson-Niemann technique. It throws out the 26.5695. And then this table for figuring out what exactly that means. And we'll talk a little bit about how to interpret that after lunch. But this really is, again, literally point and click. It's not difficult to do. And you would have seen almost nobody do this before 3 years ago, and now I'm finding it quite routinely. And I think once you get to know this, you'll wonder, why do we do the pick-a-point approach? What's the point of that exactly? Because this is just washes your hands entirely of the arbitrary problem. All right. So let me talk a little bit about conditional process modeling in the time that remains, and I'm going to shoot for taking 15 minutes at the most so that we'll have a little bit of time for questions. This is where things get very exciting, as I promised, where I tend to run out of time, and probably where your attention is also starting to wander. And where things get a little bit more complicated. But if we step through it at a reasonably comfortable pace, I think you'll get the idea, and if you don't, there's things you can read about this to get the detail that you might miss in the next 15 minutes or after lunch.
I made up the word, but I can't make up the history. The history is what it is. It's been around for a while, the idea of combining moderation and mediation analytically. It's gone by a variety of names, the distinctions of which are important, but also confusing. For instance, moderated mediation versus mediated moderation. These are both forms of conditional process modeling. It was probably sometime in the middle part of the last decade where there was this sort of explosion of papers that now started talking about this idea of combining or integrating analytically a model of moderation with a model of mediation. And then sometime around the same time as actually these papers were being written, we started to see these tools that actually made it possible. But I think this is still new enough. You're seeing it a lot now, but I think there hasn't been a whole lot of written guidance out there for how to do this well and to do it right. And so that was part of the motivation for the book that I will have out next year, where you'll get a little bit more detail about this. So not new by any means, in principle, but in practice, relatively recent. So here's the idea. If we use the term moderated mediation, what does that mean? Well, that means mediation that is moderated. Well, we've talked about indirect effects as being these products of paths in the mediation model. Those themselves are effects, and as we talked about, all effects have certain boundary conditions. So in principle, either A or B or both could be moderated in some fashion, right? And if that's the case, if A or B or both depend on another variable, then that means that the indirect effect itself must be moderated. So it's a variety of scenarios you can imagine. One in the case in which maybe A is moderated by some variable, or perhaps B is or both at the same time. And you could even have circumstances in which the direct effect is also moderated. When you have moderation of a path in a mediation model, it's not sensible to talk about the indirect effect, because there isn't one. In that case, indirect effects become functions of other variables, in the same way that X's effect is a function of a moderator in a simple moderation model. So too would the indirect effect be a function of the moderator. And here's this is what I meant when I was saying, if you don't quantify indirect effects, you don't have the opportunity to model them. So by thinking about indirect effects as interesting quantities that you should quantify, then you are in a position to be able to start thinking about understanding variation in indirect effects by person, situation, context. Just to give you a few examples of how this could work. So here are 3 examples of a sort of interesting situation, and I'm not convinced actually makes sense, but people were talking about it. In which a variable X moderates its own indirect effect. So an indirect effect of X could depend on X itself. That is not nearly as common as this, in which the effect of X on M is proposed as moderated by some 4th variable. Some people call that a first stage moderated mediation, because it's the first stage of the mediation component, the effect of X on M, that's moderated. Here's what some people call second stage moderated mediation, in which the second stage of the mediation component from M to Y is moderated. You could have the same variable moderating both the first and second stage, which is called, not surprisingly, first and second stage moderation, or moderated mediation. So let's play around with this, with the attention to activity or planning data. So what we'll do here is we'll tie together what we've already done. We'll tie together the mediation component. That was the part without the age. And we'll tie that into the moderation component that we did earlier, in which age was moderating the effect of planning on activity. We'll put those all together and tie them all together in one analytical model. This is a moderating mediation model in which the indirect effect of intentions on physical activity through planning is proposed as moderated by age. So how does this work? Well, here's what the model looks like in statistical form, right? This is a conceptual model. This is not, you couldn't put this into, say, something like Amos, draw this and expect it to work. It won't let you even draw this. Here's how you would have to set it up analytically. And this is a simplified version. There are a variety of covariances and other things that you would want to put in here as well. But here's the statistical model. And to break it up a little bit for you, well, first of all, notice that on the sort of on the left, the upper left part, we've got the mediation component with the two covariates. We're partially got these time one variables. And then in the bottom there, we've got the moderation component, where we've got age and the product of age and planning as predictors as well. That model is represented in the form of two equations. Those equations are there at the bottom. Where essentially every variable that points at a particular outcome, whether that's M or Y, gets its own weight. It's basically just a bunch of just two simple regression models. All right, so let's sort of break this apart. So here's our conceptual model on the left and the statistical model on the right. Okay, so here, so our first part, we've got a model of M, which has really only one variable of interest to us, that's intentions. We're interested in predicting planning at time 2 from intentions at time 1, and along the way, we're going to parcel out prior information about activity and planning. So that's what the model of M is picking up. We're going to need that because we're going to need A1. We're going to need to know what that is. We don't care so much about A2 or A3. The second component, model Y, is pretty much everything else except that path from X to M. So those are our two equations and where they fit into these diagrams. And I think I've got some stuff to break this up even more for you. Yeah, I do. So here's the moderation component of that combined model. So the moderation of the effect of planning on activity by age, well, that's essentially the three predictors of Y in that statistical model, and that's represented in the form of the various coefficients B1, B2, and B3 in the model of Y. And in the bottom equation, I've simply substituted in, for the effect of M, this thing theta, where I've defined theta as B1 plus B3 V. From the logic earlier, how we can break that material in the first equation in the box down into a smaller component. So we can then, with all this information, with these coefficients estimated, B1, B2, B3, and A1, we can now start piecing this all together and talk about this thing called a conditional indirect effect of X. So an indirect effect is the product of paths. In this case, it's the product of A1 and theta. Theta is now a function. Theta is a function of V. That function being B1 plus B3V. So the indirect effect is therefore A1 times the quantity B1 plus B3V. So that's conditional in the sense that the indirect effect is dependent on V. That's why we call it a conditional indirect effect. Does that make sense? It's just a simple, fairly simple idea. A simple principle for path analysis in which the indirect effect is a product of paths. If one of those paths is a function, you've got to substitute the function in for what was before just a simple coefficient. All right, estimating A1 is easy. We could do that in any regression program, right? In this case, it's 0.177. And we know that we can estimate everything else fairly easily as well. B1 and B3 come out from a regression predicting activity from planning, the covariates, age, and the product of age and planning. So B1 here is minus 0.311 and B3 is 0.013. And that gives us everything that we need. Take those and tie them together. The conditional indirect effect of X on Y through M is the product of the effect of X on M. That's A. It's actually A1. And the conditional effect of M on Y given V, which is theta, that function of V. So the conditional indirect effect of intentions on activity through planning contingent on age is that 0.177 times that function of V. The table at the bottom just arbitrarily selects the various values of age. A1, of course, is not a function of V, so it's constant across any value of age you choose. Theta is a function of V. That's the conditional effect of planning on activity, condition on age. So that's going to depend on age. And then you tie the two together, multiply them together, and you get the conditional and direct effect for different values of age. Those are descriptions. We want to apply an inferential test. We can bootstrap that just like we could bootstrap an indirect effect in a simple mediation model. Same exact procedure. We just repeatedly resample the data, calculate the indirect effects, conditional indirect effects in every resample, and generate the confidence intervals in the same way. Computationally intensive, but no more so actually, because the bootstrapping is still being done on a single model. The conditional and direct effects themselves, you can calculate as many of those as you want. Each time you run through it, you just pick values of age and put them in. We do have a direct effect in this model as well, but this is not conditional. There's nothing in this model that allows the direct effect to be moderated, so it's merely that C1 prime path. It's the effect of x on y in the model of y. So that's an unconditional direct effect. We put all this together, oh, sorry, no, you've already seen this, how we can estimate C1 prime. That just comes out of that model of y. Put all this together visually, you can sort of see what's happening here. So the red line is the direct effect. First of all, on the left, you have to notice that the left axis is the effect of intention on activity. So that's how changes in intention, differences in intentions are related to differences in physical activity later. Well, there are two paths of influence. The direct path, which doesn't operate through planning. That's not conditional on age, which is on the x-axis. So that's just a horizontal line at 0.176. The blue line is the conditional indirect effect. That's a representation of that function, A1 times the function V. And then what you can see is that mechanism through planning is smaller among among the younger and older, stronger among the older. So it seems like this mechanism of planning is more relevant or important to linking those attentions to behavior among the older people. Among the younger people, it's primarily driven by something else. The dotted lines are the endpoints of a confidence interval for various values of age, and I've selected 25 of them to generate this plot. This plot does not come out of any computational program that I've written. It sort of requires you to run something through multiple times and then piece it all together. So that's a visual representation. Back in 2007, Chris and I, along with Derek Rucker, wrote a paper that goes into the theory behind this, and then we produced an SPSS-only tool that makes this easy to do. And process, however, makes ModMed, that macro, pretty much obsolete, because process does everything that one does and a whole lot more. So here's an example output. Again, you'll see this in more detail after lunch, where it estimates the models of M, the models of Y. And then most interesting, down at the bottom half is where we get the direct and the indirect effects. And notice as well that it's automatically, in this case, selecting various values of the moderator, which are defined by various percentile values, calculating the indirect effects, conditional on age, and then generating a bootstrap confidence interval with those values of age that are, again, arbitrary. So you'll have a better sense to look and think about that after lunch. Okay, so we're a little bit over where I was hoping to go, but let me just summarize. So I've essentially said all this before. Effects function through some kind of a mechanism. That's mediation. And I think what I've tried to illustrate here is that mediation analysis has changed since 1986. We don't do things that way anymore. All effects are contingent on something. That's probably something that doesn't need to be said, but it's an important part of the story. if these are both true, and they are, then focusing on one or the other is going to be complete in some way. You're going to have analysis that's only part of the story. But now we have these analytical methods available for combining moderation and mediation in sort of modern ways, and it can be done, as you'll see after lunch, with software that you already use, and it's a lot easier than maybe it would be apparent from the last 15 minutes. It really is not difficult at all. So as I said, this information is available. There's a white paper which you'll find on my webpage, which talks about some of the theory behind all this, and then again, it'll be in my book coming out in 2013. And then my webpage is fairly easy to remember, and you'll find a lot of information about the work I've done there. At this point, then I'll just stop and take as many questions as you want to launch in my direction.
Within your process, is it possible to get the Johnson-Damon use the Johnson-Damon technique to estimate these conditional process models?
We built that into ModMed, I think, sort of naively, because in order to do that, in order to legitimize that procedure, you have to make assumptions about the sampling distribution, which is exactly why we don't use the Sobel test. The Johnson-Damon technique is essentially a version of the Sobel test. But because I personally don't believe that one should be using the Sobel test, I'm uncomfortable programming the process to use a method which sort of requires you to make this assumption, which I very publicly have rejected. So, in principle, it's possible. The process doesn't do it. And if it did, I wouldn't recommend its use anyway. But it's an easy extension. You can do the same thing. You can derive the standard error of a conditional indirect effect, tag a p-value onto that, making assumptions about the distribution, and then work backwards. You can say, well, what's the critical value of z needed, and work back here and figure out, well, how do I derive the Johnson-Damon significance regions? And that's what we do in the 2007 paper. But I think looking back on it, neither of us agreed that was that good of an idea.
In the example you just worked through is kind of a stupid question. You focused on moderation of the relationship between M and 1. Was that just a decision you made, and that's what I'm going to examine in these analyses? Why did you not look at moderation of the relationship between X and M?
Oh, I could have. And in any model you can conceive, one could always think of things that could be moderated and possibly moderators of that. And at some point you have to stop and say, I'm just going to do what I think is sensible right now, or when I have the data or the theory to back up. In this particular case, I was doing this to respect the authors of this paper. I was essentially doing this because that's what they did. Actually, the story is a little bit more than that. The third author of the study is a woman by the name of Amelie Wiedemann, and I gave a symposium with her at APS last week. And in our email discussions, I wanted to show her a way that I would analyze her data. And so I just did what she did as a means of showing her here is a different approach to doing it. And I just kept that example for this talk. But in the end, yeah, I mean, you could choose any path you want and think, well, what could be moderating this? And if you can come up with a basis for that being justified and you've got the data, why not? I just happened not to do it in this particular example.
That was a decision you made theoretically, not one that you had to, not that one that was driven by the data results and the results you got.
It was a decision that Amelie made, and I just was doing what they did. What you'll find, and this is sort of the beginning of what I'm going to talk about right after lunch, is that the tool that I've created is very addictive, and it does encourage this kind of data exploration. Whether that's a good or a bad thing is up to you to decide. I personally don't have any problem with fishing around, and I can talk about my ethics of that if you want at some point. But it makes it very, very easy to say, oh, I wonder what happens if I try to moderate this path by that variable and see what happens. And point and click and done, and you can see.
With regard to the Johnson-Damon critical regions, do you think there's a case to be made for controlling those regions for multiplicity, for controlling that overall type 1 error?
there actually is already a literature on that. There's a name for that. It's called the pot of modification. ModPro, one of my macros, actually implements that. The concern is, the inclination is to say, well, at any value within the, you could say that if I chose any value within the region of significance, then that effect is statistically significant at p of 0.05, but technically speaking, no, that's not true. And so in order to get around that, you need to be a bit more conservative in what counts as a significant effect. And what that does is it'll tend to make the region smaller. But if I recall the literature, the person who proposed the modification acknowledged that it was probably more conservative than most people would be comfortable with. So the ModPro macro, which does implement that modification, is there. But
do you recall if they addressed that? Do they use like a probability-based rule for testing?
There's some kind of multiple test-based theory, probability theory that goes to the derivation of really what the critical value should be that you're then working around. And that's ultimately all that the macro does. It finds, well, what's the new critical value to deal with this? And then it works from that instead of an uncorrected critical value. But with all of those approaches to multiple tests, you know, that you're going to lose power doing that. It's just a trade-off between the types of errors you're willing to make.
You can be less conservative with some adjustments than others.
Sure. Right.
If there are no questions, I think lunch is going to be brought out or served, and I would also encourage you during the lunch hour. The HACRC, we also support student research, and we have a number of student posters outside. Please engage your students. Our board just doesn't bring in people like Dr. Hayes once a year to speak. We support student research here, and we've got a number of exciting student posters that are in the process of being completed. Some projects are further along than others because funding just started for them in January. But please engage these students. They're more than interested in hearing from you, and would love to get any feedback that you may have. So with that, let's reconvene at 1 o'clock. Thank you.
So just to think about why these prior values are important, this path is now estimating how people who differ in their intentions differ in their planning after accounting for what you would have expected their planning to be given their prior intentions. So we can say that people who differ in intention are planning more than you would expect them to have been planning given their prior planning. So that's one way at getting at, that's one way of thinking about change. It's one model of change in which you think about change as deviation from an expectation given a prior state. The second model in the output will be the models for B and C prime. So B is now the effect of planning at time 2 on activity at time 2. Now think about the value again of adding in these controls. We would expect that people who are planning earlier might be engaging in more activity later. We would also expect that people who are engaging in more physical activity later probably were earlier as well. So this path is now picking up people's physical activity above and beyond what you already know from their prior activity and their prior planning. So this really reflects something that's unique to information obtained at time 2 with respect to predicting activity independent of what they were doing earlier. So that's much closer to being able to satisfy, although it doesn't entirely, the condition of causality involving temporal sequencing. it also eliminates all the other potential things that could be correlated with both planning and activity, because those can serve as sort of proxies for all kinds of other things that might be producing these associations spuriously. The last section of the output is a little bit larger. In fact, we've skipped over one output. I think in your output that I handed around, you also have a total effects model. So that's the model predicting activity from intention as well as the covariates, but without planning in the model. I don't have that here, but I do have it in the abbreviated end part of the output, where we see the total effect here, the direct effect of x on y, as well as the indirect effect with a bootstrap confidence interval. So in effect, what process is doing for this model is it's sort of a glorified regression routine, right? Rather than having to run these regressions and then, how are you going to possibly generate bootstrap confidence intervals in SPSS without a tool like this? You're just not going to be able to. So it's really just making the process of doing these regressions repeatedly and saving the information as it goes very, very simple. Any questions so far about anything I've talked about? Any problems with getting process to work? Any problems generating errors? Everything is going okay? It's so easy now. You kind of just don't want to listen to me anymore. You just want to start playing around, I bet. Feel free to do that. If your mind starts to wander and you want to bring in your own data, go ahead and do that. I won't take offense. All right, so let's keep moving though. We're going to now talk about using process for moderation questions. So much for tape. All right, so we have a moderation component of this broader model. Now, even though this is our full model, we don't have to model it all simultaneously. We could just pull out this one piece and take a look at that. So that's what we'll do. We'll estimate this moderated component of the model and see what process can give us about the nature of the association between planning and activity as moderated by age. Okay, so here's how that part of the model looks in conceptual form, right? So M, Y, and V. V moderating the effect of M on Y. Now, for reasons I'm about to talk about, here's the conceptual model, but I've listed planning and age as X and M. Ignoring that for a moment, this is essentially the conceptual representation of that part of the model, where we have the effect of planning on activity moderated by age, and we've got a couple of other variables that are predictors of activity, these three here. So that's what this looks like. So we've got that moderation of the effect of planning by age with a bunch of other predictors. Now here's this is the reason why I wanted to point out the X and M. Right now in our bigger model, that's M and V. But the labels that we're using are arbitrary. And the way process is programmed is that it expects to see the focal predictor as X and the moderator as M. That's the way you're going to have to set up the command when you do moderation. Mathematically, what we're going to be doing is a part of the full model. We're just having to adjust to the fact that process is programmed to expect X, the focal predictor to be X, and the moderator to be labeled M in the command structure. So here's the command. Notice we have, let me move to the statistical model. We have 6 predictors, one of them being a product of 2 of those predictors. Now notice we have, let's see, 1, 2, 3, 4, 5. Right, no, I'm trying, 7. We have 7 variables, right? 6, but we have only 6 listed here. The reason for that is when we estimate a moderation model, and this is model 1, process is going to automatically create the products that it needs for you. You don't have to do that. It'll do it for you on its own. So as the process command is set up, it sees, okay, so X is the focal predictor. That's the variable whose effect we're interested in. Y is the outcome variable. And then M is the moderator. And it's going to know that to estimate this model, we're going to need a product of X and M. But it's just going to do that for you. You don't have to do that. It's going to automatically take care of that part of the estimation process for you. It's not going to actually create it in your data file. You'll never see it. But it's there. Okay, so my template with process for moderation, for simple moderation, model 1, requires me to list the focal predictor, the moderator, and the dependent variable. Everything else is just additional options that I've added here. I'll talk about the quantile, the JN option in a minute. So if you were to go ahead and run that command, you'll get the second output that I've given you. I will leave this up for a minute in case some of you need to type that.
Can you read that off, Andy?
Sure. It says process vars equals plan 1, plan 2, intent 1, active 1, active 2, age, / X equals plan 2, M equals age, Y equals active 2. Sorry, I forgot the /. Did you get those? / COEFFCI equals 1, / JN equals 1, / quantile equals 1, / model equals 1. Actually, I think it's in the top, on the second output at the top, now that I think about it. Is it there? I thought I included that. Maybe I didn't. Okay. So with any luck, you should get output. This is a somewhat more condensed output in the sense there's only really one model here because we have only one dependent variable. That's physical activity at time 2. So there's our statistical model, and here it all is in this one nice little output. From here we can pull out B1, B2, and B3. Most important, though, is do we actually have evidence of an interaction between age and planning? And as you can see, we do. That coefficient B3 is statistically different from 0. So it's sensible to talk about then planning's effect on intentions as being moderated. Notice, as I was telling you, it's automatically creating a product term, and it's just arbitrarily labeling it int_1. So that's what you see here. This little key down here just tells you what that actually refers to.
Those interaction terms centered?
We'll talk about centering in a minute. They are not currently. You could center them if you want, and process will do that for you. Process will also automatically generate the proportion of the R squared that's due uniquely to the interaction. So if you're someone who likes to do things hierarchically, you'll have that change in R squared attached to the interaction, but hierarchical entry isn't necessary. But here's that output if you wanted to see it. All right, so as I talked about before, that doesn't by itself mean a whole lot. These are just numbers. How do these map on onto the phenomenon, the pattern of results? There is a plot option. This is to help you generate a graph. It won't actually generate one for you. But if you tag on this plot option, /plot equals 1, what it will do is it'll generate a little table. It'll select values of x and m, and why it chose these values will be clear in a minute. It'll choose values of x and m and generate what the estimation is for the outcome for those combinations. And because we've got controls, the standard procedure is to set those control variables to their means when you generate those estimates. So this you can now put into whatever graphics program you like to generate a table or a figure that looks something like this. I actually generated this in SPSS. So this is a visual representation of this. You don't even need to if you've got the ability to map these numbers into some kind of a visual space in your head. You could sort of look at this and see what's going on without actually generating the figure itself. Although your reader's not going to be able to read your mind, you might want to generate something like this for them. ModProbe also automatically implements, you actually can't tell it not to do this, it'll automatically implement the pick-a-points approach to probing an interaction. This is built into models 1, 2, and 3. If you give it a moderator that's quantitative, by default, if you give it no other instruction, it'll estimate the conditional effect of x on y at values of the moderator defined as the sample mean and plus and minus 1 standard deviation, a very common convention. It does that automatically. If it sees there are only 2 values of the moderator and it looks at the data, and if it only sees 2 values, it'll say, okay, well, your moderator is dichotomous. So I'll give you the conditional effect for those 2 groups, the conditional effect of x on y in those 2 groups. Process, and this is not either of those because I used the quantile option. I have, so the quantile option gives you a different way of thinking about slicing up the data. So the problem with the mean and plus and minus 1 standard deviation, you might have experienced this in your own lives if you've done this, is sometimes one of those is outside of the range of the data. For instance, if you've got a really skewed moderator or something like that. So if you just sort of mindly apply this procedure, you can get yourself into trouble by estimating effects that are outside of the range of your data. So the quantile option, what it does is it actually will look at the data. It'll figure out what the 10th, 25th, 50th, 75th, and 90th percentiles of are the moderator. And it'll generate the conditional effect of x on y at those values of the moderator. So it does that for us automatically, which is why we see these 5 values. So 31 is the 10th percentile in age in the data set. 38 is the 25th percentile, and so forth. So here we see that except among the younger people, and this is defined arbitrarily as those that are around 31 years old, there's no effect of planar non-intention, but for everyone above that, you see some evidence of an association that's positive between between planning and action. These are arbitrary, of course. If you want to apply some kind of label, you might think of this as the median, so that's sort of moderate. Then you've got sort of low and high, and then you've got, well, really low and really high, if you want to put those kinds of labels onto it. The nice thing of those are always going to be within the range of the data. Always. No chance that it'll be outside of the range of the data, as it could be if you just use the mean and plus or minus 1 standard deviation. Process also does have an option for specifying, you could put in whatever value of the moderator you want. You could put in, I want to know what it is for people who are 32.65 years old. Just there's an option in process you could use for doing that, and it'll give it to you. And you can just see the documentation for how to do that. So is everyone clear on what this is? Okay. It will also implement, process also implements the Johnson-Neiman technique, and that's merely by specifying that we want the JN method implemented by setting the toggle to 1. This works only for quantitative moderators because that's the only sensible way it makes any sense. The Johnson-Neiman technique doesn't apply to dichotomous or categorical moderators. So when it sees that a moderator is quantitative and you've specified JN equals 1, you'll get this table. So what it's doing here is it's deriving the point of transition between statistically significant and not at a given alpha level, which you can specify, although it defaults to 0.05. It says the point of transition is 34.1255. So something's happening at that point of age. And then what it does is it takes the distribution of age and it just randomly slices it, not randomly, it systematically slices it up. And the point of this is not to look at this like a whole bunch of hypothesis tests, because that's not what it's designed to be interpreted like. What it's doing here is by showing you the p-values attached to the conditional effect at various values of the moderator, you can see what's happening at the point of transition. 34.1255, it's inserted into the table, and you can see here that that's the point at which the conditional effect of planning on physical activity, that's this, is just statistically significant at 0.05. And notice that everywhere above that, it's statistically different from 0 and positive, whereas everything below that, it's non-significant and even negative. So you can see what's happening is that those people who are younger than roughly 34 years old, there's no association between planning and physical activity, but among those older than 34, the association is positive.
Table also, you see the possibility of a nonlinear association?
Nonlinear where?
Well, through the effects, I assume that, like, you know, if it affect asymptotes at a certain level.
It wouldn't. It simply wouldn't ever happen because the model is programmed. It's linear interaction, so you'd have to put in a different function or implement a different function which process doesn't implement. So it could be that that's the reality, but you'll never see it with process because it's constraining the nature of the interaction to be linear. I'll talk a little bit about mean centering and standardization because it did come up, and it's an important lesson anyway. There is a big controversy in the literature. It's actually not that much of a controversy among methodologists. When you have a model that includes a product of two variables in that model, as is the case in a linear interaction model, the conventional wisdom is that you should mean center, in this case x and m, first, prior to generating the product. Some people argue not mean centering, but standardizing, which is actually a form of mean centering combined with a rescaling. So the idea is that whether you're an advocate of centering or standardization, you shouldn't be estimating this model, you should be estimating one of these. So this is the mean centered model, and this is the standardized model. There are four primary reasons that people talk about why you need to do this. One of them is the idea that our models are more accurate, and more importantly, that power is increased for testing interaction because the product is going to be highly correlated with the variables that define it. And that's certainly true in the sense that there will be strong correlations between X, M, and their product. However, it turns out that matters not at all. It's actually a myth. Power is not changed at all by centering. You will still have a test of the interaction that's mathematically identical whether you choose to center or standardize. Just isn't necessary. A second reason people give is that their interpretations of B1 and B2 in that model are more meaningful. And that is frequently true, although it's not necessarily true. Now to think about what I mean by that. In this model, what does B2 estimate? Well, what does B1 estimate? B1 is a conditional effect. This is the effect of x on y when m is equal to 0. Now, if m can't be 0, if it's outside of the scale of measurement or it's simply not possible, then that B1 is estimating something that really is meaningless. If you mean center, B1 now estimates the effect of x on y when m is equal to the sample mean. That will always be meaningful. The same is true with standardization. B1 will estimate the effect of x on y when m is at the sample mean. That would usually be more meaningful. Is it always the case that centering or standardization will produce B1 and B2 that's more meaningful? No. It depends on whether 0 is a meaningful value on the other variables. If they are, then those coefficients are estimating meaningful and interpretable quantities. The third is that doing so reduces the likelihood you'll misinterpret your findings. That I say perhaps, because if you know how to interpret a centered or a standardized versus an unstandardized solution, then the choice isn't going to change whether you interpret it correctly or not, because you'll know what you're doing. But if you're not comfortable with what happens when you mean center or standardized versus not, you very well may end up interpreting a model incorrectly. Specifically, and if this is related to 2, many people will talk about B1 as what they call a main effect, which it's not. It's not a main effect in an analysis of variance sense. If you think that it is, and you don't mean center, you're going to make a big interpretational mistake. If you know what you're doing, you won't make that mistake. But if you're not comfortable with the interpretational principles, it would be easy to misinterpret B1 as a, quote, main effect. So if you get in the habit of always centering, you'll never make that mistake. You'll never end up interpreting a parameter that's outside of the range of the data and therefore meaningless. So in a sense, then, perhaps it will reduce the likelihood that you'll make a mistake if you don't know what you're doing. If you're not comfortable with the subtleties of the interpretation of a model with a product as a predictor variable, centering can keep you out of trouble if you just get in the habit of doing it. And then fourth, people talk about rounding error. When you have predictor variables that are highly correlated, back in the old days, when computers were less sophisticated than they are now, computations involving highly correlated variables can produce rounding errors which can sort of propagate through a set of equations, and you can end up in situations where you're getting inaccurate model information because of the rounding error. But that's just not a problem anymore. Computers are now more sophisticated. They're less susceptible to problems generated by rounding error. And so I just don't see this as a concern these days. So the moral of this is that there's no need to center. There's no need to standardize. It's not a requirement. You can do it if you want. But the benefits of doing so are generally either misstated or overstated. Collinearity, multicollinearity has nothing to do with the reasons why we might choose to standardize or center. Whether you choose to center or not is up to you. I give a whole lecture on this topic where I go into much more detail as to why all these things are true. But I'll have to leave you with that for now. If you are someone who wants to center, you do have that option in process. There is a center option. Just turn it on. And what process will do is for any model, any of the 74 models which involve the need to construct a product of 2 variables, it will first mean center those variables before it generates the product. And all output will be interpreted with respect to the centered, should be interpreted with respect to a centered metric at that point. So there's nothing really interesting here, except this looks actually identical to the output that you have. What's changed is that now age is centered. But whether you center or not, that's not going to change the conditional effect of x on y. It's still going to be the same thing. It's just that the parameters end up getting rescaled. But the end output of the model is going to be identical. And process does give you the notice that certain variables were mean-centered in that analysis by listing out which variables those are. And it'll know what to do. If you say center, it'll know which variables to center, which ones are involved in products. It'll leave those that aren't involved in products alone. All right, so our last model then is going to be this one that integrates moderation and mediation into a conditional process model. This is model 14 in process. The second stage moderation of the indirect effect by a moderator, a single moderator. There's not a whole lot new to talk about here. We've got the same variables in the model, the same variables serving as their functions of m, y, and x, but we now have v, which is age, so we've had to tell process that. Everything else is just extra with the exception of model 14, which it's going to expect. So if you were to go ahead and execute that command, it'll take care of all the hard work for you. It'll run all the models. It'll do all the centering if you ask for it. It'll generate all the conditional indirect effects. It'll do all the bootstrap sampling for you, and it'll do it all pretty quickly. And then give you the output, which you have in front of you. This is the third output. Can I advance? These commands are written on your output, on the handout I gave you. Any problems in interpreting why I'm setting up the model in this fashion? That is the process command, the form it takes. There's the statistical representation of it, just as I showed you before lunch. The actual models involved, which variables are predicting what variables are products, and so forth. And then here's our output. We have two dependent variables in this model, m and y, so we need two models. Here's our model of planning. That looks identical to our other model that we estimated because that part of the model is the same. So not surprisingly, A is the same as it was before. This should look familiar to you, right? Because this is actually the same as that model 1 output we saw earlier, because that part of the model is identical. That is the moderation component combined with a bunch of additional predictors. So this is really identical to the model 1 output that you saw earlier, because that part of the statistical model is identical. So we have our direct effect as well as all the terms that are required to construct our conditional indirect effects. Point of controversy or discussion. Here we do have evidence that age moderates that a path. People often ask me, well, is that a requirement? Is it a requirement that I have evidence of an interaction between a moderator and some other variable in order for me to go through this process of estimated conditional indirect effects? My argument would be there's nothing wrong with that if it's not, but a more parsimonious model would fix that path to be unmoderated if you don't have evidence for it. But an argument could be made that It's just a hypothesis testing procedure. It's fallible. You can never prove a null hypothesis true. So we shouldn't necessarily insist on evidence of moderation before we start talking about conditionality of various indirect effects. All right, so here's the conditional indirect effect. You've seen this before, although I've done the computations to 4 decimal places instead of 3, but otherwise this is the same as what I talked about before lunch. Here's our A path, our theta, which is the conditional effect of m on y for various values of age. We could calculate that conditional indirect effect for any value of age we choose and generate a bootstrap confidence interval for those values. This is kind of like a pick-a-point approach, but applied to moderated mediation instead of just moderation. And then here's the output you get relevant to the direct and indirect effects. The direct effect, it's relatively straightforward. It's just that C prime path. Right, that's this in that model. And then because we've used the quantile option in the command, we're getting the conditional effect of intention on activity through planning at the values of age defined as the 10th, 25th, 50th, 75th, and 90th percentile. Because, again, because I chose to use the quantile option. Had I chosen not to use that option, I would have 3 values that it lists. The values of age at the mean and plus and minus 1 standard deviation. If age were dichotomous, it would show us only 2 conditional indirect effects, 1 for each group. So we have the age, we have the conditional indirect effect itself, and a bootstrap confidence interval. So here we see that, again, as we sort of already know, except the most young in the sample, the conditional indirect effect is positive. So except among the most young is defined as in the roughly the age 30 category, 31. That indirect effect is not statistically different from 0, but it's positive everywhere else. Okay? It starts to get pretty routine after a while, huh? I mean, you sort of figure out how this works. You see the output. As long as you understand the concepts, this is pretty routine. When I teach this class at Ohio State, or if I run full day or 2-day-long workshops, we would go into a variety of different forms of conditional process models, talk about how the various pieces are put together. We could go into models with multiple mediators. We could go into models with multiple moderators and multiple mediators. Process can handle all of those types of problems. So when you look at your documentation, remember, all of those models, you can have multiple mediators at once. And some of those models have multiple moderators on different paths. Sometimes there are multiple moderators on the same path. Sometimes you have 3-way interactions in the models. There's a lot of ways that you can piece things together, and process can handle a lot of things. It can't do everything. There are some models in which you're going to have to move into, you're going to have to get your hands dirty and move into a structural equation modeling context. I recommend M+, because it can do everything I'm talking about here if you know how to program it. So process is great if you've got a model that fits into the box. If you have a model that deviates from any of the 74 boxes I've given you, well, you'll either have to make a compromise, or you'll have to start doing some actual work and move to a different software platform and do things the hard way. So as I mentioned, all this material is available on my website. In addition to process, you'll also find all my other macros there, although, frankly, there's no reason to use any of those other macros that I've now integrated into process. But they are there. They're out there. You'll hear people talking about them. You'll see people citing them. So those are there as well. Again, I mentioned there is a white paper, which you would now have if you used the USB drive. I gave you a copy of this, but you can download this from my webpage. It's about a 40-page paper which talks about what process does, and it gives 4 or 5 different examples. And then this will be the topic of the book again that I've said now probably with the 4th or 5th time will be out sometime toward the end of this year or early next year. So any questions that you have about anything I've talked about, anything about process, any of my odd idiosyncratic perspectives on mediation or moderation? Uh-huh. Sure. Okay. Mediated moderation focuses on the conditional nature of an indirect effect. So how an indirect effect is moderated. So that's moderated mediation. If you think of mediation and indirect effect in synonymous ways, moderated mediation really means moderated indirect effects. So your interpretive focus, your estimation interpretive focus is on estimating the indirect effects and how the effects vary as a function of a moderator. So that's moderated mediation. Mediated moderation says, what's the mechanism through which an interaction operates? So we have moderation. Well, what's the mechanism that carries that interactive effect? So you might think about it in these terms, where think about a product between two variables as representing the interaction, and you're interested in the mechanism through which that interaction operates. So a mediated moderation model, and you see these around all the time. People doing this. The way this is generally set up looks something like this, where you have a model in which your total effect is focused on the total effect of a product, and you want to estimate the indirect effect of that product. So this is the statistical representation of mediated moderation. So that would focus primarily on estimating that indirect effect, where the indirect effect is the indirect effect of a product. The problem I have with this is that the product itself is meaningless. It's not a measure of anything. Remember where that product came from. That product came from thinking about x's effect as a function of m. And when you do the math, you put the function in, then do the algebra, the product pops out. So the product really is just a mathematical corollary or outcome of the way that we think about, the way that we can build flexibility into a model so that the effects aren't unconditional. If we want the effect of x to be conditional on m, we set up the conditionality and do the math, and it turns out the product is needed in that model. That's what gives it the flexibility. But the product itself isn't meaningful. The product has no substantive interpretation. And if the product itself has no meaning, then what is the indirect effect of a product? I would say it's meaningless. It turns out, and I actually do go into this in the white paper, that indirect effect of a product does have an interpretation mathematically, but it turns out that the interpretation that it has can only be meaningful if you think about it in terms of moderated mediation. And I show that in that white paper. It turns out that the indirect effect of the product is the change in the conditional indirect effect of x on y through m as the moderator is changing by a unit. Now that sounds like a mouthful, and it is. But the point I'm going to ultimately make is this. That mediated moderation model, it turns out, is identical to this model. Mathematically, these are the same. But what this model does, is we still are clearly focusing on a variable that we are interested in. In this case, it's an experimental manipulation, a simple two-group manipulation. We want to understand that mechanism through which that effect operates, and we're appreciating that that mechanism is moderated, but it's moderated in both the direct and the indirect effect. This, to me, will always be meaningful to talk about, because it places the focus where it belongs on x, which is meaningful. The product isn't. I don't expect what I'm saying here to necessarily make sense. There is a little bit of math involved, and when I teach a whole class on this, I spend a good lecture and a half on this distinction. But if you read about it in the white paper, you'll hear my argument as to why mediated moderation just is not interesting. People do it, and you can do it with process. You could do it in Model 4. How would you do it in Model 4? Let's take a look. How would we estimate mediated moderation as Model 4 in process?
Would you have to actually create an interaction variable?
Yeah. So create the product. Now think of the product as X. So the product is X. And now we have the two variables that define the product as covariates. And what we'll get out of it is the indirect effect of that product. Process model 8, which is what this is, I'm using this only because I happen to have these slides available. The context, the example, I know you don't understand. I'm just using this visually. It turns out that model 8, which is what this is a moderated mediation model. Because it's mathematically equivalent to a mediated moderation model, I added a section of the output where it actually will show you all the stuff relevant to moderated mediation, but it also calculates the indirect effect of the product. So you can get output relevant to both. The reason why I did this is because I know some people might want to look at that, but I also hope that they can think about this in a different way, in a way that ultimately I think makes more sense. So that's, in a nutshell, the distinction. I don't think mediated moderation is substantively interpretable. It's mathematically interpretable. You can show that the indirect effect of the product can be conceptualized in terms of differences in conditional indirect effects, but in order to have that interpretation, you have to be thinking about it in the mindset of moderated mediation, not mediated moderation. These terms are confusing. I mean, it's a reasonable question to ask, which is why I'm just using the term conditional process modeling. And both of those would be forms. Mm-hmm.
So if we're trying, or if we're proposing to use this type of analyses for a project that we're working on, or some type of research that we're doing, how do you calculate the power that they're going to want to know what your sample size has to be able to do this? Is that calculated in any different way, or do you just use regression?
Well, in the sense that certain of these models, really you can think about in purely regression terms, or really just in terms of simple mediation models like this one was. In principle, you could apply some basic rules and guidelines in simple mediation analysis. But power in these kinds of models, well, first of all, I'm not a big believer in power. It's not that it's the concept, it's not that I sort of pretend it doesn't exist or something. I mean, I know that it's out there and I know it's meaningful. But I just see it as I see it as almost a kind of voodoo that we do to show people that we're not wasting their money. But there's so much guesswork involved in it that I just think it's mostly hand-waving. I mean, it's important, yes. I mean, if you're design studies, don't do things underpowered. So in principle, I get the idea. But I think that in practice, it turns out to be just semi-educated guesswork. That said, there is a small literature on power in mediation analysis. These can be complicated models. And so the way that people, if I'm writing a grant, if I'm contributing to a grant in some way and I need to do a power analysis, I'll usually do it through a simulation in which I put in sort of reasonable parameters for a sort of minimally detectable, an effect that's sort of minimally detectable in the sense that I would care. And then I would simulate to see how large the sample needs to be to get that detect with a certain degree of power. But that means for the specific nature of the model, actually hard programming it and seeing what it takes. There's no simple math, no simple table that you can use, with the exception of one paper by Fritz and McKinnon in Psychological Science. In 2007, they have a little sample size table for detecting indirect effects for very simple models. And the magic number is 500 about. If you want to bootstrap, you need about 500 to 600 people to detect a moderately sized indirect effect with bootstrapping. If you want to go to Barron and Kenny, you need thousands. And sometimes, in my experience at least, granting agencies mostly care about whether you seem to know what you're talking about, whether you can get a number and it seems like you know why you got that number. The specifics of how you went about it just requires whatever skills your statisticians have to bring to the task. I think in the end the answer doesn't matter as long as it seems credible. Mm-hmm.
Let's say that you have people here that don't want to type up the syntax, and they just prefer the dialog box. How would you sell people on typing up the syntax? I mean, what are the benefits of syntax over point-and-click?
I have a slide for that too, although I don't know where it is exactly, so I'll do this off the top of my head. Well, the first thing, when I talk to our grad students about that, the first year, the first stats course, we teach them syntax. And among the reasons we give them is, one, you're going to embarrass yourself if you don't know this, because your advisors, your grad student collaborators, they're going to know this. So if no other reason, just out of fear, you should learn it. That said, we talk about the reasons why pointing and clicking means you're going to be doing a lot of more work than it seems than if you're doing syntax. So even though syntax there might be some startup costs in terms of learning it and typing stuff out. In the end, when you do like what many people do, which is collect a third of your data, and then run some analyses, and then collect another third, and run some more, and then, it turns out you miscoded this variable, so you got to redo this analysis. If you're just pointing and clicking everything, you've got no record of what you've done. You've got no way of redoing it easily. When you've got a syntax file, you simply make the change, you run it, done. It serves as documentation of your work, so that others can see what you've done. I insist that people who I'm working with, whenever there's a grant involved, that they write code. Because not only do I want to have that code, because for all we know, we're going to do the study again when you're long gone. I want to be able to generate the same analysis you did. I also am. I don't want this to sound terrible. I trust that students can do well, but I'm going to verify that they do, and so I want to see the code to make sure that mistakes aren't being made. Was that 3 or 4 so far? I could probably come up with a few more. What I find is, I find that when students pick it up and they appreciate it, then they understand that that's valuable. And I'll point and click now and then. It's okay. Everybody does it once in a while. But in the end, when I'm getting sophisticated, I want to document my work. Because when I write code, or when I do analyses, particularly in complex analyses, when you move to other programs, it's like you're not. After 6 months passes, you're not sure what you did really originally. Whereas it serves as a way of sort of refreshing your own memory as to what you were thinking when you did this analysis. If you have no record of that through point and clicking, then you're just kind of lost. And you certainly can't handle your work over to others. And people do disappear, they die. I mean, you do need some kind of a record of the work that's been done, in my opinion. I'm terrible at documenting my work, but I know at least I've got a folder filled with version 1, version 2, version 3 of my syntax, and that if I must, I can recreate what I've done. Anything else?
If there are no questions, then thank you for coming out. This is a game changer. We're happy to have you here and to spend 4 hours teaching us about process, and people who want to talk with Dr. Hayes can do so at Eddie's house this evening at 5 o'clock and tomorrow morning at 12 o'clock.
Sure.
Thank you.
Sure, a pleasure.